Hey everybody, we're here talking about deconstructing polynomials using factoring. So what do we know about polynomials? Well, the fundamental theorem of algebra tells us that for an nth degree polynomial, that polynomial is going to have n zeros, and that's over the complex numbers. Okay, if you start talking about the real numbers or the rational numbers or the integers, it's likely going to be less than n. But over the complex numbers, every polynomial has n zeros, which means it also has n linear factors. Okay, so if we have a polynomial of degree n, okay, in standard form, ultimately we can rewrite that as a product of these linear factors. Okay, and there's a couple different ways to do that. This is a common one, right, where we have x minus whatever each zero is, and then the leading coefficient out front. Okay, a little note about that is that, something like 2x minus 1, the zero's 1/2, okay? And so there's, a couple different ways to write those. Okay, so this just highlights the zeros themselves with the leading coefficient of every linear term just coming out front. Okay. So what do we do here? Well, we've got a third degree polynomial, so it's going to have three factors, 3 zeros, 3 factors, and we're told that x minus 5 is a factor. So that means that x equals 5 is the zero. So I'm going to go ahead and use synthetic division to go ahead and factor out this factor and see what we are left with. Okay, so we bring down the 2, we multiply 2 times 5 to get 10, we add vertically, we multiply, and we add vertically again, and multiply diagonally, and there we go, boom, 0, just like the remainder theorem tells us we should get, right? The factor theorem says a remainder of 0 gives a factor, right? So we're left with 2x squared plus 5x minus 3. Okay, and we want to go ahead and factor that. So we're looking for the factors of -6, right? 2 times -3, that add up to be 5. Okay, and so that's going to be +6 and -1. So we can use grouping to rewrite this. Okay, the 5x as 6x minus x. And now we can find the common factors in each column and row. So in this first column, the common factor is x. In the second one, it's 3. Okay, in the first row, it's 2x. In the next one, it's -1. So that gives us our other two factors, right? So now we can rewrite our polynomials x minus 5 times x plus 3 times 2x minus 1. And again, if you want to find the zeros of those, you can set each of those equal to 0 and find it, right? You're going to get 5, -3, and 1/2. So this next one, this one's a little more complicated because it's a 4th degree, number 1, but also we are given a complex root. But that actually helps us out because if we know one complex root, we know that its conjugate, in this case 1 minus the square root of 3i, is also a root, right? So this, we can find the factors of each of these, multiply them together, and find a quadratic with real coefficients. So let's go ahead and do that, right? So we'll start with x minus 1 plus the square root of 3i, and multiply that by x minus 1 minus the square root of 3 times I. Okay. And then whatever's left is going to be some other quadratic. So we're going to have a quadratic multiplied by a quadratic. Okay, so let's go ahead and find this one. First thing I want to do is actually distribute the negative and think about these as trinomials instead of binomials. Okay, the reason being it's going to be a lot easier to multiply these as trinomials. If we multiply them as binomials, we're going to have to take an extra step and multiply stuff out. Okay, so I'm going to have x minus 1 and minus the square root of 3i, x minus 1 and plus the square root of 3i, right? This illustrates the flexibility and versatility of the area model. Okay. All right, so we go ahead and multiply x squared minus x and minus the square root of 3ix. Next row, we have negative x plus positive 1, positive square root of 3 times I. And the last row, we've got positive square root of 3i times x, negative square root of 3 times I, and negative Well, square root of 3 times square root of 3 is 3. I times I is I squared. All right, so let's figure out what we've got here. Well, the x squared is x squared. Okay, the negative x and the negative x make negative 2x. The negative 3i, that's square root of 3ix, and the positive square root of 3ix cancel, and we're just left with positive 1 here. Positive square root of 3i and negative square root of 3i cancel. And then I squared, that's negative 1. Negative 3 times negative 1 is positive 3. And when we add these up, we get x squared minus 2x plus 4. So there's our quadratic that represents these two complex roots. Okay, so now we need to divide this quadratic into the fourth degree polynomial and see what quadratic is left over. Again, I'm actually going to use the area model to do this. Okay. Since I already have my first trinomial right here, okay, oops, I'm going to go ahead and write our quartic outside, 2x to the fourth, negative 11x cubed, negative 8x squared, positive 32x, and minus 120. Okay, so we're going to end up with some other quadratic over here. Now, the nice thing is that we know a couple of these right off, like this 2x to the fourth is the only thing that goes there, and this minus 120 goes there, and we can put those there with confidence because we already know that this quadratic is a factor. Okay, so we're not going to have any remainder or anything like that. So we can basically start from both ends and meet in the middle. It makes it nice and easy. So we can multiply by x squared 2x squared to get 2x to the fourth, and then we multiply, keep going, we get negative 4x cubed here, 8x squared. So that's that row. All right, now we already have an idea of what's going on down here. Okay, 4 times 1 will give us negative 120. That's negative 30. Okay, so we can multiply across here. We're going to get positive 60x, okay, and negative 30x squared. All right, now the key to making this work is going to be using this diagonal right here. We know this diagonal should add up to be negative 11. We've got negative 4, so this needs to be negative 7x cubed. And when we do that, we need to multiply by negative 7x here. Okay, here's negative 28x. Here's positive 14x squared. And we're just going to double check. 60 minus 28 is 32. 8 and 14 is 22. Minus 30 is negative 8. So all of these go together, and here we go. Here's our other quadratic factor. But the thing is, right, we still need to factor that. Okay, so we're going to multiply negative 30 times 2 to get negative 60. Okay, and we're trying to figure out what are the factors of negative 60 that add up to be negative 7. And that's going to be negative 12 and positive 5. So again, using the area model and grouping, I have my 2x squared. I'm going to rewrite my negative 7x as positive 5x and negative 12x. And then we have our negative 30. So we find our common factors in our rows and columns. In this first row, it's 2x. First column. Second column, it's 5. First row, it's x. And the second row, it's negative 6. Okay, and so now we can add these to our factors that we had because of our complex numbers. Okay, we've got x minus 1 plus the square root of 3i, x minus 1 minus the square root of 3i, and then x minus 6 and 2x plus 5. Again, the zeros are going to be 6 and negative 5 halves. You can set those equal to 0 and solve. All right, so there's our 4 zeros that correspond with our 4 factors. Okay, our 4 factors that go with this. All right. So the last thing we want to take a look at is the rational root theorem. Okay, so another way to write all of our, if we think about having a bunch of different linear factors that we multiply together, it's going to look something like this, right? And so this is the other way to think about having the coefficients attached to them instead of out front. But we could solve each of these and see what the zeros are. Right? This one we'd subtract e and divide by a, so we get negative e over a. This one we would get negative f over b, and this one we would get negative g over c. Okay, and let's just say there's n of these, so we have some sort of polynomial like this, right? When we multiply all of the initial terms together, right, whatever's in between, okay, a times b, the leading coefficient of every linear factor is going to multiply to give us the leading coefficient of our polynomial. And the constant term of each of our linear factors is going to multiply to give us the constant, right? So we have this interesting result that any sort of rational solution, right, okay, it's got to be rational, so it could be an integer, could be a fraction, but it can't have square roots, it's not going to be a complex number. Any of our solutions that are going to be rational, they're going to have this form right here. Okay, and when we take a look, the a, the b, and the c come from factors of the leading coefficient. The e, the f, and the g come from factors of the constant term. So the rational root theorem tells us that if we have rational roots, they're going to be of the form where the numerator is a factor of the constant term and the denominator is a factor of the leading coefficient. So let's see what that looks like. We have this example right here. It's a cubic. It's got 3 solutions, and I'll tell you, this one can actually be factored pretty easily just using grouping by factoring the common factor out of the 2 terms and going that way. So you can check that out if you need to practice that. But just highlighting the rational root theorem, we're going to take the fact that our solutions are going to be of the form the factors of 6 over the factors of 2. Okay. So factors 6 are 1, 2, 3, and 6, and again it can be any any of the combinations that make it positive, and then plus or minus 1, plus or minus 2 at the bottom. Now we start actually making combinations of all these. First off, if we take all the numerators and divide it by 1, we just get the values in the numerator. Okay, so there's some possibilities right there. And then we start looking at fractions. 1 over 2 plus or minus 1/2. 2 over 2 is 1. We already have that. 3 over 2 is not there. And then plus or minus 6 over 2 is 3. We already have that. So we have a lot of solutions here. And so how do we figure this out? Well, we use our skills all together. All right, so we'll take a look at the graph. We're going to determine what looks likely, right? Like I can see from here, okay, we've got negative 1.225. I'm not sure exactly what that negative 1 or positive 1.225. There's some symmetry there. And then we have positive 2. So positive 2 is one of our solutions, okay? Right? It's right there. So I've narrowed it down, and it's not any of these whole numbers here, and 1.225, it's not any of these fractions. So the only one is going to be 2. So let's go ahead and use synthetic division to factor that out. Okay, bring the 2 down, we multiply, we get 4. Add, we get 0. Multiply, we get 0. Add, we get negative 3. Multiply, we get negative 6. And add, we get 0. So yes, x plus 2, or x minus 2 is a factor. All right, and what we're left with is 2x squared minus 3. And we can set this equal to 0 and solve by taking square roots. So x equals plus or minus the square root of 3/2, right? So we end up with x minus 2 times x minus the square root of 3/2 and x plus the square root of 3/2. And I'm not worried about rationalizing either of those. Okay, so there we go. We've factored it completely, starting with that rational root theorem. So try that out, and good luck.